Okay, next is Mark Suder from TMC Technologies NASA IV&V program for PSP.
Thank you, Subodh. As Suod said, I'm Mark Suder. I'm a systems engineer at TMC Technologies at NASA's IV&V facility. So what I'm here to talk to you today about is a project we've worked on, and just try to make a catchy title. I called it GNC Glue and 42, Independent Dynamics for Independent Testing. So bottom line up front, why did we do that? At NASA IV&V, one of the big keys is independence. We're managerially, financially, and technically independent. We do IV&V on software, but of course, not software across the agency for NASA, and it has to have a systems focus because it's controlling systems. So one of our NASA IV&V engineers actually saw an opportunity when he was looking at the PSP project, and that was there is a single truth and flight software guidance and control MATLAB simulink model that was developed by the project that they're using then to test and will end up being the auto-coded. They will do auto-coding to generate the flight software code. So what his opportunity was can we have an independent truth source? So that's where this project then was born out of. So probably a lot of people are familiar, but I just put a little bit of background on PSP. It's going to go closer to the sun surface than any spacecraft before it. It's going to have some pretty brutal heat and radiation conditions. Has this giant heat shield on the one end of it. This engineer, he would tell me this looks like an ice cream cone to him. So on the top end there, where the ice cream would be, is this 4.5-inch thick carbon composite heat shield, and that's going to have to withstand temperatures up to something like 2,500 degrees Fahrenheit. So as you can imagine, guidance and control pointing is going to be incredibly important. Another one of the things he would say was the basic goal of GNC for this is live, die, live, die, live, die. You got to keep pointing that heat shield in order to protect everything behind it. So as far as I thought I'd list just quickly the sensors and actuators, most of them are pretty typical on a spacecraft. It's got 2 star trackers, 4 reaction wheels, some solar limb sensors. That's a little bit different. They're scattered around the base so that if it does tilt off, they'll be able to detect that it's the attitude's not what it needs to be. Typical digital sun sensors, IMU, thrusters, and then the solar arrays can actually move in a couple directions. When it gets close to the sun, they call it flap and feather. They can flap in behind that heat shield so they're protected, whereas when it gets out towards aphelion, they'll flap out so they can gather more solar power, and then they can actually feather in order to track the sun. And then finally, there's a high gain antenna with 1 degree of motion on it. So as far as the independent dynamic source we selected to use, it was 42. It's a package that's developed by Eric Stoneking at Goddard, and he's simulating the spacecraft attitude and orbital dynamics and control. And he intends it, from his documentation for all kinds of different studies, concept studies, ops, whatever. And what's key for us then was the architecture. The way it's architected, you can see down there's kind of some brown boxes down to the right where you can actually call out to flight software. So within the sim step, every time you make a step in the numerical integration, you can actually call out to the flight software and then take data back in. And so we then are, and I'll describe this in a few minutes, actually took advantage of that architecture. So a little bit more background about independent verification and validation, and then JSTAR, which is the group that I work for. So independent verification and validation performs analysis of all kinds of software artifacts for the large missions across the agency. So all kinds of analysis like requirements analysis, design analysis, static code analysis. We've heard some about that earlier today. Test procedure analysis, test results analysis. So then the group that I work for, the JSTAR group, we're more experts in simulation. So what we do then is build these tools that are used by analysts to do their job. In this case, we're building in most cases, what we build are dynamic execution tools to allow them to do dynamic testing. So as I said, one of our IV&V analysts kind of had this idea, and he actually started the test bed, but then he brought us in so that we could, add some more of the software engineering to it and continue it on. And so what we did then was we stepped back a little bit. He already kind of had that basic 42 and auto-coded GNC algorithm hooked up. But we stepped back and said, let's try to modularize this, because what we've had to do is, as new versions of the flight software have come out, upgrade them. So we modularized it to make it fairly easy to be able to do that. And then he had just started, I think, 1 or 2 of the sensor models, so we ended up developing the rest of the, when I say models, it's more the hooks, the glue, and I'll talk about that in a minute. So the glue, the PSP guidance and control is a CFS style app. They're using CFS on the spacecraft, so that's a single application developed by the project, and it uses the CFS software bus messages to bring the sensor data in off the bus, process it, and then actuator data out. As I mentioned earlier, the 42's architecture makes it pretty easy to call out to flight software at each integration step. And so then what we really did was write this glue code. So we take the dynamics data from 42's real world, positions, velocities, attitudes, wheel speeds, so on. And then there's a couple different types of conversions we have to do. One is you have to get it into the right coordinate frame. Usually it's in some body frame. We convert it to the sensor frame. That's not too bad. But then the sensors typically don't put out like a sun vector. They put out counts for this or that. So then we end up turning it into that type of data that goes into the actual messages, just like the GNC software would get from the software bus. And then after it processes, it spits back out actuator controls. We interpret them and then feed that back to actually forcing the actuator control within 42, whether it's torque a motor or fire a thruster or so on. So the way we designed this part of 42 was already built with the concept that you would have input files, you'd tweak them, set up the scenario you want, run it, and then generate a list of output files. And so we kind of just extended that. So some of the files already existed. We were putting the orbit in. We set up an ephemeris file for upload for PSP. There's all kinds of parameters, of course, about the sensors and their positions and so on the spacecraft. So that data is coming straight out of their parameters data or design documents for those sensors and actuators. We also allowed the 42 had the capability already to have command files, but then we've added more commands to that. So you can say, okay, now I want to simulate that this accelerometer is offline or something like that. And then at the end, another one of Sam's ideas was the output files are just text, but hey, why not make them CSV files? Because a lot of this data, we're writing it out, and it's every time step we'll write out a new line, but it's a lot easier to understand in a graphical format. So making it CSV, then Excel, you can just bring it up, and I've shown there in the bottom right. Then you can actually graph wheel speeds and see what's going on, how the momentum's building up, and so on. So I had a little video to kind of show an actual part of a run. Let's see if I get this running. It was running earlier. So this scenario, what we've set up is it's an aphelion scenario. I don't know if nope, shouldn't have got out of that.
That's okay. Let's see. In the slideshow.
So what we have is an aphelion scenario, and I've just set it up with an attitude where the heat shield is pointed directly at the sun. However, at aphelion, it's actually not. That's not the standard attitude.
Yep, it's running now.
And so what you'll see is as it plays, you can see that we're full closed loop control. The sensor data is going in. It's figuring out where the sun is. what the sun vector should be based on sensor data, and then starting to actually control the reaction wheels in order to make it slew to the attitude that's the default attitude for that distance from the sun. And you can also see we've added in, the ability to actually control the solar arrays, so the solar arrays also are tracking the sun. They're feathering to actually track the sun. So here you actually have some visualization, but if you then want to dig into more, okay, why does this look like it is, or what exactly happened, then the power is that there's these resulting output files that you can look at later to better understand the behavior. So advantages and disadvantages to this approach that we took. We are using the PSP auto-generated code, and actually Sam had started with just the auto-generated code. We backed up and are actually using more of the code, because there's some hand-generated code that actually does the CFS interface to the auto code from MATLAB and Simulink. So we're using all of that. The way 42 is, as I said, it's set up so that it's fairly easy to get the data in and out as it calls the PSP flight software, and we're calling it at the appropriate rates for the different types of sensor data and the different processing rates, the minor frame and major frame rates that are within their software. We ended up then with pretty extensive CSV reporting of inputs, outputs to the GNC flight software, intermediate results, because there's a lot of intermediate results they have within that model, and then the 42 truth data as well. So you can look at them side by side and say, okay, well, here's what truth was, here's what the sensors, readings told you, here's what was interpreted, and so on. And the disadvantage, obviously, this did take some time to develop. Took, I guess, a fair amount of GNC expertise. I'm not really a GNC expert. I had to, there's quite a bit of learning to get this all working. As far as uses, so now IV&V has an independent test capability to be able to independently test the software, and especially a lot of the things our analysts will try to do is look at adverse conditions. What happens if this piece fails, that piece fails? How's the software going to react? So now we have a tool that they can more easily do that kind of analysis. And kind of a benefit that wasn't thought of, from the start, but then actually came out was, when the analysts would use it, then they could actually see, okay, they really see, rather than just on paper seeing specs, or requirements, they actually then can see the sensors and the actuators actually moving. So the bottom line, of course, is this is providing an independent testing capability based on a need identified by what would be my customer, the IV&V organization. So future, as I mentioned, there will be IV&V analyst testing. But then as far as other missions, this was a little bit different type of simulation than our group had typically done before. And so it was kind of a pathfinder also to show that this kind of capability is, we do now have that ability. We've shown that we can do this kind of work. So that's pretty much the end. Are there any questions?
You have a question?
Thank you for the presentation. Did PSP use 42 themselves in any part of their GNC application?
No.
It would reduce the independence, obviously, if they did.
Yes.
Anyone else has a question?
Yeah, I'm Mike Furrow. I'm the mission software engineer for PSP. I know currently, this was kind of news to me. Currently, IV&V is not actively using this for PSP, so I guess you guys just developed it, and they're going to evaluate it in the future. Is that correct?
The plan is to use it in the future. Yes.
Okay. Thank you.
Thank you. Well, thank you. Thank you very much, Mark.
Okay.
Yeah.